My name's David Romps, and I'm going to talk about a simple analytic toy model that connects various properties of convective aggregation to the degree of aggregation in the domain. So when we talk about convective aggregation, or when we study it in cloud resolving simulations, we see that there are connections, there are tendencies, relationships between the relative humidity of the domain, its lapse rate, and the precipitation. So what we would like to answer here is whether we can develop a theory that connects these three things to the degree of convective aggregation, which I will define later as the fraction of the domain that has the convecting, precipitating moist patch. So first, let me tell you about some old results, which are that we can derive analytic solutions for radiative convective equilibrium, properties such as relative humidity and the lapse rate, using some really basic ingredients. And these are results that go back to a 2014 paper. So the ingredients are as follows. First, we need to model the atmosphere using bulk plume equations. So we'll have one bulk plume equation for convection. This just means that at every height, we'll assume that the convection has homogeneous properties. And likewise, for the environment, it will also have homogeneous properties for that sinking air, and so we will use a bulk plume equation for that as well. Another ingredient that we'll use is to assume a steady state. And we'll also use the zero buoyancy plume approximation, which says that at each height the convection has the same temperature as the environment, which is an empirical fact that we see is adhered to closely by the real atmosphere. And we'll, of course, specify some amount of entrainment or detrainment, so this turbulent mixing between the rising convective plume and the descending environmental plume. And we'll add in two other things. We'll add in the Clausius-Clapeyron relationship for water vapor, and also hydrostatic balance. And those are all the main ingredients we need to describe radiative convective equilibrium. We just need to specify one more thing, which is that the mass flux going up in the clouds is equal to the mass flux coming down in the environment, so that there is no net ascent or descent in the overall atmosphere. This is a defining characteristic of radiative convective equilibrium. So given those, we can then derive analytic expressions for the relative humidity and the lapse rate. And as I said, this is old work that goes back to this paper in 2014. So what I'm going to talk about here is really an extension of that, where we've extended this to thinking about atmospheres that have steady ascent or descent, as opposed to radiative convective equilibrium, where the net ascent is zero. And here we'll be able to, again, analytically derive expressions for the relative humidity, the lapse rate, and the precipitation, or the condensation rate. So the ingredients are the same: bulk plume equations, zero buoyancy, plume approximation, Clausius-Clapeyron, hydrostatic balance, steady state, specifying entrainment and detrainment rate, things like that. The one difference in terms of setup is just that we no longer now assume that the mass flux going up in clouds is equal to the mass flux going down in the environment. These can now be different quantities, different magnitudes, so they can be net ascent or net descent, averaging over convection and environment. Okay, and what we get out of this, we get relative humidity and the lapse rate, as we did for RCE. And it also tells us how the precipitation rate varies as a function of that net ascent in the column. And this is work that came out earlier this year, earlier in 2021 in JAS. Okay, so let me show you some results. So here I'm going to show three different plots. On each of these plots here, the x-axis is this variable m tilde. M tilde is simply the total column mass flux, the mass flux averaged over convection and environment, relative to the convective mass flux in RCE. So the little tilde here is the notation I'm using to say, okay, relative to something in RCE. And here I'm talking about total column mass flux, total atmospheric mass flux relative to the convective mass flux in RCE. It's just a convenient way to normalize things. Likewise, this C here is the condensation rate, equivalently the precipitation rate, and it's relative to that of RCE. So I've plotted 3 points in these 3 panels that correspond to the RCE value. So they're all at m equals 0. At m equals 0, that's RCE, where there's no net ascent. Right? The ascent in convection balances the descent in the environment. For condensation, since this is defined, since C tilde is defined relative to the RCE value, it's just 1. So there's a value of 1 at m equals 0. For the lapse rate, we see that the RCE value has a lapse rate of about 6 Kelvin per kilometer for the choice of entrainment and detrainment rates used here. And for relative humidity, we see something about 70%. So those are old results, these analytical expressions we can get for RCE. But by loosening the requirement that the net ascent be 0, we can actually map out these values for any value of m. We see, for example, that as the column's net ascent goes positive, then we get an increase in the condensation rate. Or as we increase the net ascent in the column, the lapse rate goes down towards the moist adiabatic lapse rate. Conversely, if we force the total atmospheric column to be descending on average, and the more we do that, the more the lapse rate asymptotes to the dry adiabatic lapse rate. And then for relative humidity, we see that as we have larger and larger net ascent, we're driving the relative humidity of the column to 100%. So we can also look at these relationships and how they vary based on the choice of entrainment rate. And you see some interesting things here in terms of how the condensation rate or precipitation rate varies based on the entrainment rate. In RCE, it doesn't matter what the entrainment rate is. The precipitation rate is dictated by the total radiative cooling of the column. But when we're pushing to net ascent or descent, we see these solutions flange out, and we get different values for different entrainment rates. For the lapse rate, we see at RCE that a higher entrainment rate gives you a higher lapse rate. It pushes you closer to the dry adiabat. And that's as expected. But an interesting result at net ascent, say a net ascent of m tilde equals 1, you'll see that the lapse rate variations are small, but they're actually non-monotonic, such that the highest lapse rate is for an intermediate value of the entrainment rate. And of course, we also see that there's a dependence, naturally, of relative humidity on the entrainment rate, as we would expect from the work on the RCE results from 2014. So what are these solutions good for? Well, one could have the idea that perhaps these solutions would tell us about variability within the tropics. So if that's what we want to get at, we would want to look at different relationships that the model predicts. Say, for example, between temperature in the mid-troposphere, here at 5 kilometers, and relative humidity at that same height. So what does the model say about the relationship between those two things? Well, it depends on the entrainment rate that you choose, but you get relationships that look like this. Here I'm showing curves for 3 different entrainment rates. This is the model prediction. These are coming out of the analytic expressions. So we see that as the relative humidity goes down, we would expect a cooler temperature at 5 kilometers. So you might think at this point that all we have to do is go look out there in observations and see what the relationship is between temperature at 5 kilometers and relative humidity at 5 kilometers to see what nature's entrainment rate is. But that doesn't work. In fact, that fails for a very good reason. What we see when we look at the observations in the tropics is a flat line. we see that the temperature at 5 kilometers does not depend on the relative humidity at 5 kilometers. Now, there's a very good reason for this, and that is that the empirical property of weak temperature gradients is a very good one. It's adhered to closely by the tropics because gravity waves are efficient at smoothing out temperature variations. Now, the model, on the other hand, doesn't know anything about gravity waves. And in fact, is quite peculiar in this way, in that each solution in the model is like an atmosphere in a box. It doesn't know about other regions of the atmosphere. It only knows that it has to have a certain m tilde, a certain total ascent rate, because that's one of the inputs, and that convection has to be neutrally buoyant with respect to the environment. That's the zero buoyancy plume approximation. Because it doesn't know about neighboring columns or other parts of the atmosphere, you get these solutions that allow for this strong temperature dependence on relative humidity that is not allowed in observations. What happens in the real world is that where you have convection, that's what's setting the temperature at 5 kilometers. Elsewhere, where you don't have convection and you have larger variations in relative humidity, the temperature is still pegged to the value established by the convection. So these solutions are not good for explaining tropical variability, but they do have some value in telling us something about, in a very rough sense, the overall properties of the tropics, the overall temperature structure, the overall mean relative humidity, the overall mean precipitation rate. That's where the value lies. And they're also useful for understanding convective aggregation. So what I'm going to plot on here are plots like this one, where on the x-axis is this variable f, which is the fraction of the domain that is covered by the moist precipitating convecting patch. So what we'll do is we'll use the analytic solutions that we've derived to describe that convecting patch, which within it has convection rising up and environmental air sinking within it. And then we're going to assume that the whole rest of the domain, which is this sinking environment, is pegged to the temperature profile that's established by that convecting patch. That then allows us to describe the properties of the overall domain, the total convectively aggregated, say, simulation, in terms of this variable f. So again, these are not simulation results, these are just analytic solutions. And what we see is that as we change f, so when f equals 1, that's the non-aggregated typical RCE state, just disorganized popcorn convection. As f gets smaller, that's where we're confining the convection to a smaller and smaller fraction of the domain, so more and more convective aggregation as we go towards f equals 0. Now, no matter what f is, the average precipitation rate, the average condensation rate over the domain, shown by the dashed line here, is the same. And that's because in this model I don't have any dependence of radiative cooling on humidity or clouds. And so regardless of the value of f, the troposphere is cooling at a particular rate, and the condensation has to match that rate. And so it doesn't change as f is varied. Of course, though, as we squeeze the convection into a smaller and smaller fraction of the domain, the precipitation rate in that convecting patch has to go up. In fact, it diverges as f goes to 0. And this, of course, is a property you see in cloud resolving simulations of convective aggregation. Now, if we plot the lapse rate as a function of f, over here at f equals 1, the different lapse rates correspond to different entrainment rates. Those are the same values you derived for RCE back in the 2014 paper. But now as we convectively aggregate, we see that all of those lapse rates get smaller, and they approach the moist adiabatic lapse rate as f gets towards 0. Again, this is another property. You see that the lapse rates will tend to decrease as you convectively aggregate. And a simple model is able to replicate that basic fact. And finally, with respect to relative humidity, the solid lines here are showing the relative humidity in the convecting patch, such that as that convecting patch gets smaller and smaller, the relative humidity goes up. Meanwhile, because more and more of the domain is covered by the non-convecting descending environment, that's tending to dominate the average. And so you're pushing the average of relative humidity down towards low values, down towards 0 in the simple toy model. So in summary, we have here a set of analytic solutions for an atmosphere that has net ascent or net descent, and that allows us to describe in a very rough way the properties of the tropical mean in the real world, and also the varying properties of the convectively aggregated state that we see in cloud resolving simulations, but here just based now on analytic solutions that we can begin to probe and understand.